Hello everybody again. Now we are into the third lesson of chapter 4, which is binomial distribution, so 4.3. This will be the last video for this week, and then we'll continue next week with the last two videos for chapter 4, which will be 4.4 and 4.5. Okay, so today's lesson and next lesson, 4.4, are the two more difficult ones for the chapter. Okay, the work itself isn't very difficult, but it's trying to distinguish between what we're doing today, which is called binomial distribution, and tomorrow's lesson, not tomorrow's, next week's lesson, which is called hypergeometric distributions. Okay, the only tricky thing is trying to figure out which formula to use. Okay, so here are some, and then our fifth lesson for the chapter will compare both of them together and to remember which one to use, formula to use. Okay, so we have binomial probability distribution. Okay, so this is, sorry, rewind. In the lesson earlier, we did uniform distribution. So uniform was based on one trial. Okay, when we do binomial or hypergeometric, we're basing on multiple trials. Okay. So here, independent trials, or the outcomes, for binomial are either a success or failure. Okay, I'll explain to you when we get to the formula. Okay, some key things here. Binomial has replacement. Okay, so has replacement. So if you had a deck of cards and we were cutting a card out of the deck, we would then replace it, record the result, and then replace it. Okay, or you take something out of a bag, you look at it, record the results, and then you put it back into the bag. That would be considered replacement. Okay, so the random variable equals the number of successions in a given number of trials. Okay, so we'll talk about, when we get to the examples, I'll explain exactly what we're looking at here, what is considered the success and what is considered the failure. Okay, so we had this formula introduced in the last chapter when we did when we're doing Pascal's triangle, and then we also showed you another way to use a formula to expand and simplify binomials with higher powers. Okay, so it's the same formula that we had. So we have NCX, but I think this was an R in last chapter, but it's NCX in this one. So P to the hour X and then Qn minus X. Okay, so what does each one mean? So N represents total trials, total number of trials. Okay, X is going to be considered our successful trial. And it's not necessarily mean something's a success. It's more the trials. What are we measuring? What are we looking for? What are we looking for or measuring? Okay, so what are we looking for or measuring? Okay, and with examples that will make more sense. Okay, and then so that's successful trials. That means Q. Oops, sorry, rewind. Sorry, that was X, right? Successful trials. Then P is the probability. I don't know how to spell probability. Probability of success. Okay, so what are we looking at, and what is the probability that it will occur? Okay, so X is what we're looking at, kind of like the outcomes that we did, and then the probability of those outcomes. Okay, but specific for the ones we're looking at. Okay, then we have Q. I'll go over here. So Q is the probability of failure or non-success. Non-success or failure. Okay, so we have N, total number of trials. X is the successful trials. Okay, so what we're looking for. So let's say we were choosing a number between 1 and 10, and we wanted to choose 7. So we would say, how many times does 7 come up? So that's what we'll be looking at. Okay, and then what is the probability of that 7 coming up? So that'll be probability of success. And then lastly, the Q is the probability of non-success. So what is the probability of getting all the other numbers? Okay, so again, if I was picking through a number through 1 through 10, and say I wanted 7, we want to see how many times 7 comes up. What is the probability of 7 coming up? And this would be the probability of everything else coming up. Okay. All right, then we have expectation. Okay, so we learned in uniform distribution and what was it? Probability distributions in 4.1 and 4.2. Our expectation was for it had the sigma symbol. Okay, but for binomial and our next lesson, hypergeometric, the EX or the expectation has a new formula and it's just N times P. Okay, so N is total number and P is probability. Okay, so it's a much easier formula to use. It's just N times P, so total number times its probability. Okay, number 1. Okay, a card is repeatedly cut from a deck and replaced. So keyword replaced, that means it's going to be binomial. What is the probability that in 10 trials an ace is cut once? Okay, so we want to know if we had the probability that in 10 trials, so we have multiple trials. So multiple trials, that means it cannot be uniform. So, and then we have replacement, so that's binomial. So we want to know that an ace is cut once. So in 10 trials, we want an ace to happen once. Okay, so let's go here. So going back to our formula, the N represents the total number of trials. So how many do we have? We have 10. So we want 10, choose, and we want to have how many successful trials we want? Well, we just want 1. We want 1 for an ace. So it's just 10, choose 1. And then in brackets, so again, 10 trials and we want 1 ace. Okay, now we move to the next part. So multiply by P, and P represents the probability of it occurring. So what is the probability that we get an ace? Well, the probability of ace, there's 4 of them and a total of 52 cards. Okay, so you could put 4 over 52, or you could put 1 over 13, the reduced form. Okay, and then doing our exponents is x, so P, probably P to the power of x. So what's our x here? It's 1. Okay, and then now we're multiplying by the probability of non-success, okay, or failure. So what is the probability of receiving any other card? So any other card would be 48 out of 52. Okay, so 4 aces and then the remaining cards. Okay, so when you plug this into your calculator, you get 0.37 or 37% chance. Okay, so if I cut a card from a deck of cards 10 times, I should get an ace once 37% of the time. Okay, now increasing this. So now we want to say, what's the probability that we get an ace 3 times in the 10 trials? So again, so we have 10 trials, but now we want an ace 3 times. So now we're going to multiply by the probabilities. So the probability that it will occur will still be 4 out of 52. And the probability that it will not occur, or the non-success, would be 48 out of 52. Oops, I forgot something back here. Apologies. So we had our x is our exponent here. So x, and then the exponent on top of the q is n minus x. So it'd be 10 minus 1. So this would be 9. Okay, so I forgot to put that there. Okay, going back here. So again, this is going to be x. So our x in this case is 3. And then the exponent on the next one would be 10 minus 3, which would be 7. Okay, so this is a probability. So when you plug that into your calculator, you get 0.03 or 3%. So if you cut a deck 10 times, there is a 3% chance that you could have 3 aces in those trials. Okay, number 2. Mr. Mackenzie has 4 children. Not really, but in this case we do. I do. Has 4 children. Consider the probability distribution for the number of boys in the family. Okay, so A, identify the discrete random variable. Well, the variable we are measuring is the number of boys, because we said what is the number of boys. So this is your random variable. Okay, then 2, or B, calculate the probability distribution. So there goes that keywords again, probability distribution, and hopefully you remember you have to do, that is right, you have to do a chart. Okay, so I have that on the next page. So I'm going to draw the chart up here. So for B, so again, the chart is the outcomes, which is X, time, and the next column is the probability, which is P at X. Oh, dog wants to say hi again. It's Coco. Okay, so our outcomes. So if I were to have 4 children, what are my outcomes with regards to the number of boys? Okay, so if I had 4 children, what are the probability of, or what are the outcomes I could have? So, and 4 children, I could have 0 boys. I could have 4 girls. Or I could have 1 boy, 2 boys, 3 boys, or all 4 could be boys. Okay, so those would be my outcomes. Okay, now that's where it kind of gets a little bit messy. So going back here, so how do we know this is binomial? Well, this is multiple trials. So we could consider that these 4 children, each one is a trial. Okay, so we'll say that there are trials. If it was just one child, then it would just be, you have 0 boys or 1 boy. Okay, then we could do, then we'd be able to do, it's called, uniform distribution. Okay, but now we're having 4 trials. So 4 trials, now we're having multiple trials. So then it has to be binomial or hypergeometric. Okay, so I forgot to put some, so very key word that I missed here, independent is a key for a binomial. Okay, so each trial is independent. So again, when we did here in the cards, when we take a card and put it back, the next trial is an independent of the next one because it's still 52 cards. Okay, here each child is an independent trial. Okay, so if I have, say, a girl first, that does not affect the gender or sex of my next child. Okay, so say I have 2 girls, then those 2 girls will not affect the sex of the 3rd child. Okay, so each child is its own trial. Okay, it's independent. They don't affect each other. Okay, so that's how we know we're doing binomial here. Okay, so probability. So these are all trials, so then we have to use the formula. So first we have 4 children, and in this case, our x is what we're measuring. Okay, so our x here is 0. Okay, so we're saying what is if we have 0 boys? Okay, then we're going to multiply by the probability. So the probability of having a boy in general would be 50%. Or in this case, you could put 1 over 2, or I'll just put 0.5. It's just a little bit easier to plug in your calculator. Okay, and then in the exponent is our x, which is 0. And then, so we consider this success. In this case, it's not really a success having a boy. It's just what we're measuring. Okay, so we're measuring what is the chances of having a boy, and now what is the chances of having a girl. So having a chance of having a girl would be 0.5. Okay, and then the exponent would be 4 minus 0, which is 4. Okay, now we're going to do that to each of them. So now we say out of the 4 children, what if we have 1 boy? So then we have 0.5 to the power of 1, because x is 1, and then 0.5 to the power of 4 minus 1, which is 3. Okay, I'm going to continue that all the way through. 4 choose 2. 0.5 is in the brackets. Now the exponents become 2. Then 4 choose 3. We have 3 and 1. And then 4 choose 4. Power 4, and 0.5 to the power of 0. Okay, so when you plug them all into your calculator, you get 0.0625, 0.25, 0.375, 0.25, and 0.0625. Okay, I'm just going to hold it there for a few seconds so you guys could take a look. Okay, so that is your probability distribution. Okay, so that's B, probability distribution chart. Okay, so we listed out all the possible outcomes for have children. So you have 0, but more specifically, we're looking at boys. So 0 boys, 1, 2, 3, or 4 boys out of 4. Okay, then since each one is a trial but independent of each other, we're using this formula here, which is binomial. Okay, now getting on to C. So we're going back to C. C says calculate the expectation. So since we are doing binomial, it's just EX equals N times P. Okay, and just think about this logically, it means what should you expect to have? So if I have 4 children, what should you expect to be boys? How many? So the answer should be, Marco, 2. Good job. Okay, so we expect to have 2. So just to prove that, so not N is the number of trials, which is 4, times it by the probability of having a boy, which is 0.5. So 4 times 0.5 gives us 2. So we should expect 2 boys out of 4 children. Okay. All right, moving on to, actually, I'm going to pause this one and start a new video because this one's almost 19 minutes. So I'm going to pause and then I'll put this next question into the next video.